All right, so I'm going to walk you through the summary of things we know so far about convergent and divergent series. Things we had in our last test, but that are going to come back at us again. So when do we use test for divergence? Kind of when nothing else seems to work and it's on a series. So what do? We take the limit of the nth term. If it doesn't equal 0, we get a result of divergent. If there is equal to 0, we get more work. So it doesn't mean anything. So sometimes, and again, never say converge by test for divergence, because the test for divergence checks to see if it diverges. So sometimes this test for divergent comes up when we're doing the alternating series test. When we're in the second part of it, taking the limit, and if it doesn't equal 0, then I can say this whole sum diverges by test for divergence. All right. So it's not going to be too often we'll be asked to find the sum, but I want you to recognize when the absolute value of r is less than 1, it converges, and the absolute value of r is greater than 1, it diverges. So this would be convergent because I can see that the r is 1/4. This will be divergent because I can see that r is 9/4. All right, p-test. We love the p-test, so make sure you've got it straight. If bigger than 1, it converges. Smaller than or equal to 1 diverges. Integral test. It takes a long time to do integral test, and this is the least used test, thank goodness. So it has to, the function that we get from the a sub n has to be positive, continuous, and decreasing. And if I know that the integral converges, then the sum converges. It doesn't add up to what the integral converges to. The integral diverges, then the sum diverges. Basic comparison test, used a lot. Remember, it has to be positive termed series, no negative ones. That makes it alternating. And remember, there's no squeeze theorem. There's only one inequality. So this one here would be positive because the biggest this gets is 1 and the smallest is -1. And remember, you want to take one thing up at a time. So I'm going to actually build this by taking sign less than 1, add 2 to both sides, divide both sides by the denominator, and then because I want to use p-test and I cannot use p-test on that, I would build it one more step. Then I would say that I know that this is messy, 3 over n to the 4th converges by p-test, so therefore I would get that this one converges by basic comparison test. The larger converges means the smaller converges. So make sure you work slowly and keep the inequalities going the same direction. So limit comparison test, again, has to be on positive term series. You take the limit of the ratio of the two, and it'll give you a number. If that number is bigger than 0 and not infinity, then they both do the same thing. They either both converge or both diverge. So this one is one of the harder tests, so this would be a good one if I started to do BCT. Taking off the number, this would be smaller, so 1 over n cubed. Remember, you would have to say this converges by p-test, right? A sum converges, not a fraction. So this is where BCT fails, right? So then you would have to go to the limit as n goes to infinity of your original guy times the reciprocal of my new one, right? This one. And so I would get n to the 4th over n to the 4th. That's 1. That's bigger than 0. So they both do the same thing. So that's how I would get this guy converges also by LCT. This one here, if I started with a BCT, which I would think of doing because it's just easy to pull off one number, right? That has more in the denominator, but if I'm looking at 5/3 to the nth power, that's a divergent geometric sum. So this would be a good time to do the limit comparison. Take the limit as n goes to infinity. Oops. And multiply by the reciprocal of this, so that'd be 3 to the n over 5 to the n. taking the limit as n goes to infinity, so I'd get 15 to the n over 15 to the n, right? Because I would take highest powers, so that gives me a 1. That's bigger than 0. They both do the same thing, so that must mean this one diverges also by LCT. So these were two cases where the BCT failed, that limit comparison test came into the rescue. We could also do the limit comparison test by making a new sum by taking the highest powers. So if I take a new sum, I would take the highest powers from the numerator and the highest power from the denominator. So the e to the n's would cancel. Let's rewrite this as the power to the 5 halves. So if I subtract, I get n to the 3 halves, right? This would be 2 over 2, subtract. So this converges by p-test. So now I'm ready to do the limit comparison test with this and this. So limit as n goes to infinity, and e to the n plus 4. Lots of terms here, right? So write them all down. Oops, n plus 1, multiply by n to the 3 halves over 1. Okay. So taking highest powers, so I'd have n e to the n times n to the 3 halves, right? This 4 plus 4 times this would fade off on the distance because I'm doing highest powers. This times this, e to the n, and n to the 5 halves. So the e to the n's cancel. So let's look at this again. So this n times n to the 3 halves, that would give me n to the 5 halves. Oh, look at that. It's a 1. Bigger than 0. They both do the same thing. Since this one converges, so yes, you do have to invest the time to say, therefore, this one converges also by LCT. So that's a review of all of the things that we know so far that are going to come back into play.